Dear friends, welcome back. In our previous lecture, we discussed about the characteristics of infinite wings as well as finite wings, and we related the lifting characteristics of an infinite wing with that of a finite wing, right? So we considered a lifting line theory from which we figured out that as the aspect ratio increases, right? So this is the increasing order of aspect ratio. So the CL alpha decreases, right? The lift curve slope decreases. So this is for a wing of infinite aspect ratio or for airfoil. So this lift curve slope represents an lesser aspect ratio compared to that of an aerofoil. So this is where the finite wing starts, right? This plot, from this plot we are talking about finite wings. So this is the variation of CL with angle of attack. Right? So if we can observe, so as the aspect ratio increases, CL alpha increases here. Right? So and we have related CL alpha 3D is equals to CL alpha 2D upon 1 plus CL alpha 2D upon phi E AR, where E is a Oswald's efficiency factor and is equals to 1 for, and the limits are less than or equal to 1, where E corresponds to, so E is equals to 1 corresponds to elliptical wing, right? So we know AR is the aspect ratio of the wing, of the finite wing, okay? Right. So now let's look at how can we relate, what are the drag characteristics. We haven't discussed much about drag here in the previous lectures. So let's now relate what are the drag characteristics of a infinite wing as well as a finite wing. Is there any relation between these finite and infinite wings? So that's what we are going to do right now. So we know drag. Right. So do you remember? So due to the resultant pressure distribution, so when we consider an airfoil in the flow which is inclined at an angle of attack alpha, right? So there will be pressure distribution as well as shear stress distribution. Resultant of that over this surface will be an aerodynamic force called a resultant aerodynamic force, and the component of this resultant aerodynamic force acting perpendicular to free stream is considered as lift, and a component of aerodynamic force, this resultant aerodynamic force which is acting along the free stream, is considered as drag, right? So drag is component resultant aerodynamic force which is acting along or in the direction of V infinity. Okay. Fine. And we know drag is given as half rho V square S times CD, right? So we are talking about infinite wings. We are considering an aerofoil in the first place. So let us consider this CD as, like, for infinite wings, the drag coefficient is represented by small lowercase d, right? C subscript lowercase d. So CD is the drag coefficient. So what is the contribution? What do drag do in the first place to the flight vehicle? What does it do? It will retard the motion, isn't it? It is acting against the motion. When we say it is, the flow is in this direction at V infinity, which means the body is also moving in the same direction with the same velocity under ideal conditions, right? That means the drag is acting opposite to your motion, which is retarding your motion in the fluid, right? So drag retards the motion. So what do you remember as soon as somebody talks about retardation in a fluid? So what is the property that helps this to happen? Property of the fluid that helps this to happen? Friction, fluid friction, right? The fluid friction is called viscosity. So viscosity is the major contributor for the drag. Of course, there is pressure contribution as well. So viscosity creates shear stress, isn't it? Shear stress distribution. Okay. So we understood one component of this. If not drag directly, we can say drag coefficient. So is from the shear stress distribution, right? So what is the other contribution? Let us say if there is a component of the pressure, or there is a pressure difference along the flow, right? There is a pressure difference across the body. That will also contribute towards drag. If there is a higher pressure difference, higher pressure on the frontal part and the lower pressure on the back part, so that pressure difference along the flow will also create pressure, like drag, right? That pressure difference. So we also have pressure distribution of free stream. So do you remember this pressure distribution? A typical pressure distribution over an aerofoil, right? So where there is positive pressure acting in the frontal part and then negative pressure So this is the typical pressure distribution. So higher the negative pressure, what do you mean? Higher the negative pressure is a point that corresponds to higher velocity. Am I correct or not? So that point corresponds to a lower pressure point. Higher negative pressure is nothing but lower positive pressure there. Right? So there will be a component. See, there is a pressure, higher positive pressure here and lesser positive pressure on the back side. So this will also create, this pressure difference will also create certain force, right, in the direction of free stream velocity. That is known as contribution of drag coefficient due to, or the pressure contribution of this pressure difference along the free stream towards the drag coefficient, right? Now let us consider, do you remember in the ideal flow theory when you talked about a cylinder, we assumed that there are stagnation points S1 and S2. This is the typical pressure distribution that we discussed. Do you remember that? So we have positive pressure on front and back, and negative pressure on top and bottom, because the highest velocity is equals to twice that of free stream velocity at point P at 90 degrees, right? Isn't it? So it is same, like the distribution on top and bottom is same, right? In case of ideal flow theory, and then on left and right, or in the direction of flow, the distribution of pressure is also symmetric about this object, right, along the free stream. So this will not create any drag on the object, right? But intuitively we all know that, okay, when there is an object in flow, irrespective of that, there is certain drag, you know, so this body experiences certain drag, isn't it? So this particular, though it is in flow and there is no drag and no lift, right? Such a condition is known as D'Alembert's paradox, right? So that corresponds to ideal fluid theory or ideal, yeah. Yes. Why we are discussing this? So, but in reality, even at zero angle of attack, so this we are talking about ideal flow theory. But in reality, even at zero angle of attack, there is flow separation at the trailing edge, right? That creates a pressure difference between the leading edge part and the trailing edge part, right? So the pressure difference along the flow direction creates certain force on this body along the flow direction. So that contribution is towards this CD, drag coefficient. So this drag coefficient in the coefficient form can be the drag coefficient because of friction, that is skin friction, and drag coefficient due to pressure difference, right? So what do you call this? It's in the coefficient form, we call it as drag coefficient due to skin friction. We call it as drag coefficient due to pressure difference, right? Or so this first term is known as skin friction drag. Skin friction drag, and the second term when multiplied by the other parameters here is known as pressure drag coefficient or pressure drag due to flow separation, right? Due to flow separation. Okay, so these two together, like skin friction drag and pressure drag due to flow separation, is known as profile drag. Right? Is known as profile drag here. So the CD pressure. Okay. So for an aerofoil, these are the only two contributions. Like the two contributors for the drag for an aerofoil are the skin friction drag as well as the pressure drag due to flow separation. Right? Okay. So the CD variation can be given as CD at corresponds to alpha 0 plus alpha square, right? Can be with some coefficients zeta 1, zeta 2. So this is a typical pressure like drag coefficient variation with angle of attack in case of an aerofoil. Okay. But what happens when we have a wing? Do you remember? So we talked about lifting line theory, where there is a horseshoe vertex with a bound vertex and then associated with two trailing vertex closing by a starting vertex, right? Characterized a high aspect ratio wings in terms of their lift curve slope. Right? So we can use that theory to characterize that high aspect ratio wings. Am I correct or not? So while deriving the theory, we also witnessed that there is an induced angle of attack, isn't it? For example, consider an aerofoil which is oriented at certain angle of attack, V infinity, right, at alpha. But due to this downwash, what happens is, due to the downwash, so the resultant vector will be different here. So this is your V resultant or V infinity prime, right? So which is equivalent to this. So this is V infinity prime. so induces certain angle called alpha I, right? So this particular angle is your local angle of attack. Right? Do you remember alpha L is equals to alpha minus alpha I, right? So, and which generates a lift. So say this is your lift, overall lift acting perpendicular to the overall free stream velocity, right? But because of the induced angle of attack, alpha I, because of the upwash and downwash, what we have is a change in local velocity, due to which there will be a change in local lift generation. Am I correct or not? So this, a component of this lift that is generated at that particular location, right? So because of the induced angle of attack, so we have a component of this acting in the direction of drag, right? So what we have is there is a induced drag because of the lift in the direction of drag, overall drag of the aircraft, which is L sin of alpha I, right? So CDI is equals to CL times alpha I, assuming small angle of attack, and then from thin airfoil theory, from lifting line theory, what we have is alpha I is equals to CL upon pi E AR, right? This is at the wing. If you consider the downstream, this is twice, two times of alpha I, that is the angle. That, so we will talk about that when we are dealing stability aspects during the second part of this course, right? Next, during the second semester, when we are talking about flight stability and control. So this CDI is equals to CL square upon pi E AR. So what we have in addition is induced drag, so which is due to the upwash and the downwash effects near the wing, right? Okay. So this, apart from this screen friction, see again, if you consider a finite wing, it has the tip vertices so it has tip vertices near the tip chords, right? So those tip vertices will try to drive the air along the spanwise direction, and then there is a wing, right? We have wing which creates an upwash and downwash behind, upwash ahead of upstream of the wing, and downwash in the downstream of the wing. So all three together will induce certain angle of attack, or will alter the local flow and produces this induced drag, right? So there is a contribution of lift to the drag. At the same time, there is flow, right? When there is flow, there is pressure distribution as well as shear distribution. So what we have is drag coefficient due to skin friction as well as pressure drag coefficient due to flow separation, isn't it? So the total drag here, so drag coefficient CD for a finite wing is equals to CD naught, or let us say CD because of friction, skin friction F, plus CD because of pressure drag, right? And CD because of induced drag. Okay. So apart from this, so this is okay as long as we are talking about subsonic speeds. So as we enter the higher subsonic regimes or supersonic regimes, yeah, definitely we should talk, yeah, very high subsonic or supersonic regimes, then there is an additional component due to which there is additional drag, right? So there is an additional component of drag because of shock waves, right? We'll talk why there is a shock wave. We'll very soon discuss about this. But for the time being, assume that there are shock waves at higher Mach numbers, so which will contribute towards this drag coefficient, right? So CD I. So these three put together are known as parasite drag coefficient, right? So this, and again, see, profile drag varies with alpha, right? Because so skin friction has very less effect with angle of attack, but the pressure distribution has definitely has a higher influence, right? So the angle of attack may not influence the skin friction much, but it definitely has an has a higher influence on this pressure drag due to flow separation, right? So because the pressure distribution changes with angle of attack, isn't it? So and so this particular CD pressure CD because of the pressure distribution, right? So that is why we had that variation of CD with alpha there, isn't it? So the contribution is mainly from this particular parameter, right? And again, for a very thin aerofoil, the CDF can be estimated using analytical relations of flat plate, where 1.324 upon root over Reynolds number. This is in case of laminar flow, right? So if you use this relation, you will be able to estimate the corresponding drag coefficient due to skin friction, right? So that's an approximation that we are using. So that's an analytical relation for flat plate pressure drag coefficient. So these three put together are called parasite drag coefficient. Sorry, parasite drag coefficient, which is equals to due to skin friction, drag coefficient due to skin friction, and drag coefficient due to pressure drag coefficient or pressure difference due to flow separation, right? Difference due to flow separation, and what we have is wave drag, right? Drag coefficient due to shock waves. Okay. So all three put together are called parasite drag coefficient, right? So at lower subsonic speeds, this will disappear. Wave drag coefficient will disappear. What we have is CD naught, which is equals to CD friction plus CD profile, or what we can say CD due to, so or the drag coefficient, parasite drag coefficient is due to skin friction and profile drag coefficient, plus you can say CD wave drag coefficient, but at lower subsonic speeds this will disappear. So now we can write this total CD as lift independent drag and lift dependent drag. So all these are lift independent drags, isn't it? So CD wave is because of the Mach number, not because of the lift. So CD profile is because of the pressure difference along the free stream velocity, not perpendicular to free stream, right? And CDF is due to the skin friction, which is a major contributor towards the in the direction of free stream velocity, right? Drag, major contribution of drag toward in the direction of free stream velocity. So all three put together, we can say it's a lift independent drag coefficient, right? And what we have is lift dependent or induced drag coefficient due to lift. Right. So let me name it as CD naught plus, so what is this induced drag coefficient? CDI. Okay. So this is equal to CD naught plus CDI is given by KCL square, right? Where K or CCL square upon pi E AR, right? This is your drag coefficient. So this particular equation is known as drag polar, which is also written as CD is equals to CD naught plus KCL square, where K is the induced drag correction factor, which is equals to 1 upon pi E AR. So K is known as induced drag correction factor. Okay. So this particular relation for a finite wing is known as drag polar. Right? Represents the variation of CD with CL. Okay. So if we look at the variation here, if I plot CD with CL, so how CD changes now in the lower subsonic speeds? So here you can see CD naught is lift independent drag, isn't it? So as the CL changes, we have variation in CD, isn't it? So what we can say is, so if we have CD on the y-axis and CL on the x-axis, right? What I can say is, so for example, let us consider this particular case. Right? So it's a parabolic variation, isn't it? It's a second order equation in terms of CL. So what you have is, when CL is equals to 0, the corresponding CD is CD naught. Right? This is the lift independent drag coefficient, where when CL is 0, what you have is CD. So this is the corresponding point. And then, yeah. So for the other cases where, let us say if there is, yeah, CD naught, right? So you can see the minimum point is not CD naught, it's something else. Am I correct or not? So if I postulate that with this particular equation, the minimum that I can expect, because CL can never be negative here, so the minimum that I expect is CD naught. Am I correct or not here? Isn't it? Because even CL, if it is negative, the contribution will be positive here, right? So let us assume there is a case where there is a minimum point compared to that of CD naught here, right? So let us say this is that particular minimum point which corresponds to, so this corresponds to CD minimum, right? CD minimum, and the top point corresponds to CD naught, right? And the corresponding CL for CD minimum is CL for CD minimum, right? Okay. So if we have that, then how can I how should I model it? I will change this equation to CD is equals to CD minimum plus K times CL minus CL minimum square, right? So when CL is CL minimum, what you have, the contribution from this induced drag is 0 in this particular equation. It becomes CD minimum. What you have is CD minimum. Right? So, but for modern aircrafts with moderately cambered aerofoils, the difference between CD naught and CD minimum is very, very less. Okay, so and the difference can be almost negligible, and we will neglect for the entire course. So from now we will use this particular equation, CD naught plus lift independent drag coefficient and lift induced drag coefficient, to represent CD. Okay. So this is the equation that we are going to use it for the entire course. Okay. And the equation is known as drag polar, as I told you. Okay. So let's now talk a bit about before doing that, let's solve one example problem. So why? Because I want to talk about this wave drag, right? Why there is a wave drag at higher subsonic or higher speeds. We'll discuss about this very soon, maybe in next 15 minutes. So meanwhile, we'll solve one example problem related to the concept that we just discussed. So example. I lost track of the example numbers, so you please kindly continue with the same example. In my opinion, it must be either example 8 or 9, no? Something. Either must be 8 or must be 9, right? So consider, or say consider a delta wing alone UAV with span of 1.5 meters, right? And a taper ratio of 0.167 and root chord of 0.9 meters. Okay. So the aerofoil used for the UAV has the following lifting characteristics. So alpha at CL is equals to 0 is minus 1.7 degrees, right? And or CL at alpha is equals to 8 degrees is equals to 0.48. This is the data that we have of 4811 let us say at 8 degrees. So we need to find the drag acting on the UAV flying at a velocity of 50 meters per second, right? Where the drag or the drag coefficient independent of lift or zero lift parasite drag coefficient is 0.02, right? So what are we asked? So flying at 50 meters per second and at an angle of attack at an alpha is equals to 4 degrees and 6 degrees. Okay. So we need to find the drag acting on a UAV with the given data when it is flying at 50 meters per second, right, at sea level. Let us assume the flight is at sea level and it is inclined at an angle of attack of 4 degrees and 6 degrees. Okay. This is the information that we have right now. So how to proceed with this? What we got to know from the given data is CR is 0.9, lambda is 0.1667 and CT will be approximately 0.15 meters, 0.9 meters. 0.5 where the root chord is not given here. Yeah, 0.9 meters it is given, right? So CR. Okay. So CT will be 0.15 meters. Yeah. So yeah, taper ratio is given, right? Yeah, you have taper ratio information lambda. So from which you can. So what will be the area of this wing? So in order to find the drag on this aircraft, I need to know what is half rho v square S times CD, isn't it? So I know what is the velocity at which it is flying, and sea level density I know. I need to know what is the corresponding wing planform area as well as CD at alpha 4 degrees and at alpha 6 degrees. So how can I find that? First I'll try to find what is S for this configuration. What is S? So this is a delta wing, right? So we know what is span. By this time you must be comfortable after solving those 3 examples during our in our earlier lecture. So it was about 1.5 meters, span is about 1.5. You have root chord CR is 0.9 meters, right? And CT now you got, otherwise you can say B upon 6 times, B times here B times CT plus C, B by 2 times 2 times CT plus CR, right? Isn't it? By 2. This is the area of this trapezium, and the twice the area. So B by 2 times CT, average of CT CR will be the area of this particular half of the planform, and twice of that will be the entire planform area. What I have is B by 2 times lambda times 1 plus, or CR times 1 plus lambda, right? Am I correct or not? So either you find CT separately, or then just simply use CR, take CR out of this equation. So what you have is, so out of this bracket, so you have this reference planform area in terms of span, which is given, CR is given, at the same time lambda, right? So if you substitute this, what you have is 0.787 meters square, right? So I remember this configuration. We have used it for many experimental purposes. And then, yeah, I got to know what is this. Now I need to know what is CD. CD is equals to, you can express this as lift independent drag coefficient, or zero lift parasite drag coefficient CD naught plus induced drag correction factor K times CL square. I use drag polar, right? Change from drag polar equation. Am I correct? So if I have to find CD at 6 degrees or 4 degrees at alpha is equals to 4, I need to know what is the corresponding CL at alpha is 4 degrees. Am I correct? So what is this CL? CL 3D is equals to CL naught 3D plus CL alpha times alpha, right? CL alpha 3D. So when I change this angle of attack, the corresponding CL value changes. So if I substitute 4 degrees here, I will get the corresponding CL 4 degree given CL naught and CL alpha 3D. So how do I know CL naught and CL alpha 3D? Okay, we know CL alpha 3D is equals to CL alpha 2D upon 1 plus CL alpha 2D upon pi E here, right? So we missed that Ostwald's efficiency, and also E is equals to 0.86. Consider E is equals to 0.86 is the Ostwald's efficiency factor. Now we need to find out what is AR here, right? So the aspect ratio of this wing is V square upon S, which is 1.5 square over 0.787. So if you find it, it is 2.86. Right. So 2.86 is the aspect ratio for this configuration, and we have E as 0.86, which is. So please make a correction. The CL at alpha 8 degrees is 0.79, right? CL at alpha 8 degrees. It's not CL alpha. It's CL at alpha is equals to 8 degrees is 0.79. So what we have is the following data. So the airfoil data here, right? Okay, so alpha at which CL is equals to 0. So this is minus 1.7 degrees, right? And then CL at 8 degrees. Alpha is equals to 8 degrees. So the corresponding CL value is 0.79, right? This is CL 2D case, right? CL 2D and alpha. So the coordinates here are 8 degrees and 0.79. Okay. So using this data, I'll be able to find out CL alpha 2D, which is equals to 0.79 upon 8 plus 1.7. So I'm multiplying this by pi by 180 to convert it to per radian. Okay. So that turns out to be 4.66 or 4.7, you can say 4.66. So now you have CL alpha 2D. So by substituting in that particular equation, what I can achieve is 4.66 or 4.7 upon 1 plus 4.7 over pi 0.86 times 2.86. So what I have is 2.9 approximately 2.92, right? So CL alpha 3D is 2.92. So now I know what is 3D CL alpha. So I need to know what is CL naught. Or either I can use this formulation, or what I can say is this is equivalent to CL alpha 3D times alpha minus alpha at which CL is equals to 0. Am I correct? Because for aerofoil and wing, we know that alpha at which CL 0 is same. But let us have this approach to find out what is CL naught, right? So I'll try to use this approach. So to find out what is CL naught. So CL naught is equals to CL alpha 3D times alpha minus of alpha at which CL is 0. 2.92 multiplied by 1.7 multiplied by pi by 180. So this must be close to 0. So this is 0.086. CL naught is 0.086. I have CL alpha 2D, which I have used to find out CL alpha 3D. Using CL alpha 3D, I now figured out what is the corresponding CL naught, right? As I know, alpha at which CL is 0. It was given, isn't it? So I know what is CL naught here, 0.086 plus CL alpha is 2.96, and we have variable alpha here, right? Sorry, 2.92 multiplied by, so 4 degrees, which is multiplied by pi by 180. So what is the value of CL at 4 degrees? CL corresponds to CL at alpha 4 degrees is 0.289. Okay, so what we got is CL at 4 degrees, and by substituting that value in the CD, right? So by substituting that, what I have is CD is equals to CD naught is 0.02 plus K, which is 1 upon pi AR, which will be approximately 0.12 times CL square, so is 0.289 square. Oh, what will be the answer? 0.03 is the CD at alpha 4 degrees. So I want you to calculate for CD at alpha 6 degrees. Okay. So please let me know what is CD at alpha 6 degrees. And also, don't use CL naught approach. Use the other one that we have discussed. Right? Take it as a homework problem and send it to us. Okay. So now it is clear, right? We have the data, planform like cross-section characteristics, that's aerofoil characteristics, and then data related to the planform geometry, from which we will be able to estimate what is the drag coefficient and lift coefficient at the required angle of attack, right? So now having this data of drag and lift coefficient, I will be able to find out what is the drag acting at that particular velocity, right? What is the velocity here? 50 meters per second. If we substitute that, what is the value of drag acting on this UAV at alpha 4 degrees? At alpha is equals to 4 degrees, and when it is moving at 50 meters per second, what I have is, so 0.5 times 1.2245 is the density of air, kg per meter cube. Yeah, meter cube. So density of air at sea level, and I have 50 square multiplied by CD at alpha 4 degrees, which is 0.03. 0.0. Sorry, multiplied by the corresponding cross section planform area, which is 0.787. So what is the value, Prabhajit? 36.15. So 36.15 newtons, right? So approximately I can say 3.6 kg or 3.7 kg, I can say approximately. So this is the drag that is acting. Now if I have to move at 50 meters per second, to overcome this drag I need to give 3.6 kgs of forward force, which is thrust in our case, isn't it? So I want you to find out for what happens when what is the drag that you need to overcome when you want to move at 50 meters per second at 6 degrees angle of attack for the same aircraft, right? The same UAV. Okay, fine. So let's now get back to that discussion. What happens in the supersonic flight or higher subsonic as well as supersonic flight? Okay. And we are talking about wave drag at higher speeds, higher subsonic as well as supersonic speed. So let us look at how this wave drag is coming into picture as soon as the speed is increasing, right? So same CL, let us assume we are flying at the same CL, same UAV. When moving from subsonic to supersonic, all of a sudden your drag characteristics are changing, including the lift characteristics. But let us concentrate on drag characteristics in the first place, right? So why it is happening? So how do a disturbance in fluid travels, right? That's the first thing we need to understand. So in fluids, any disturbance, right, will travel with the velocity of sound in the form of pressure pulses, right? For example, consider a pool with a pool full of water, swimming pool full of water, right? And which is calm and still. Now, if I hit that pool, if I hit a stone into that pool, so you can see there will be ripples forming around, isn't it? So let us say, consider a static fluid. Say this is where you hit the stone in the pool. So you start seeing the disturbance that we have created traveling in the form of ripples, isn't it? Am I correct or not? So similar to that, so the disturbance that we create, for example, will result in the form of pressure pulses, right? For example, what is disturbance here? Instead of now disturbance in this particular ambient condition, what can be a disturbance? If I just push air like this, or if I blow air, right? If I disturb the current state of that of this particular ambient conditions, then we can assume that disturbance will create a local pressure difference, which in turn travels with the velocity of sound in the form of pressure pulses. So this particular disturbance that travels is known as pressure pulses. These are the pressure pulses that propagates the disturbance from at a given location, which we have created at a given location. So this we are talking about a static pressure or pressure pulses in static fluid, and the velocity of this fluid or the velocity of this pressure pulse is equals to velocity of sound in that particular medium. So let us say if it is in air, the velocity of sound in air is about 330 meters per second. Okay. So now, what will be this diameter of this pressure pulse? Let us say it is disturbed at a time, like the time difference between the diameter of a, like, say if you have disturbed at time t0 and it has lapsed over a time delta t, right? Now over this period, say a delta t will be the corresponding diameter of this pulse, isn't it? Where a is the speed of sound, right? Square root of gamma rt, and speed of sound depends upon the type of medium and the corresponding temperature of that medium, right? And delta t is a time, like, after which you are interested in figuring out this particular distance that this particular pressure pulse has traveled. So that will be approximately a times delta t, right? So when you are static, this disturbance travels in all the directions in the form of pressure pulse, right? So irrespective of whether you are static or not, this is how it's going to happen. Okay. So okay, so let us now consider a general example, right? So let us assume we are driving a car or a bike, right, with a helmet on. Okay. So when you sit in the car, so when you are moving, say assume you are on an expressway, so which is about, say, your vehicle is on the expressway. Okay, so I may not be able to draw a good vehicle here, ground vehicle, definitely. So say, okay, so you're moving in this particular direction. Let us say there is a bird which is flying here, right? Okay, which is flying far ahead of this car, right? So depending upon the intensity of the disturbance, this may travel to the corresponding, like it may travel certain distance, right? Am I correct or not? But as soon as if the disturbance is in vicinity of this, so this is not affected. The flight of this insect or the bird, which is far ahead of your car, will not be affected much. So when the car comes closer to this bird, so this bird will try. So most of you might have observed this, right? So the insect or the butterfly with a good enough reflexes will try to slip over the vehicle. Right? It will not come and hit your window. It will try to slip over the vehicle, isn't it? If it have a bit of good reflexes, right? So that happens because when you're traveling, the disturbance that you're creating is also moving ahead, right? It is not that it is just moving back, right? It is also moving ahead, and it is moving in all the directions. And the flow particles ahead of the vehicle will try to adjust accordingly. So it will try to figure out where the disturbance is minimal, right? And the fluid particles in the form of these streamlines can bend across this vehicle so that they can smoothly flow over this particular body. Okay, fine. So this is true as long as the disturbance is traveling forward. Let us say if you are traveling at a much higher now, as I told you, this disturbance travels at the velocity of sound, right? Let us say you have increased the speed to a higher amount, right? So this should have a better reflexes, isn't it, compared to that, to escape into the flow. Why? Because the reaction time it will have is much lesser compared to the earlier case. Now assume a case when you are traveling with the velocity of sound, right? The moment it feels the disturbance, you will hit the bird at the same moment, right? It will hit your car, isn't it? So both happen simultaneously. So it will not have the disturbance, and that because of the lack of disturbance, this may not be able to adjust to the flow, surrounding flow happens. That is happening, right? Similarly, the fluid molecules which are ahead of your your vehicle will not be able to adjust if there is no propagation of disturbance ahead of your vehicle. Okay, so now consider the case where this particular, like, the position of this disturbance keep moving. Okay, so to understand it better, let's consider this. So let us say this is your initial point of disturbance and then you are moving in this direction, right? So let us assume this, let us analyze this disturbance at, say, this is at time t0, and this location corresponds to time 1 second, and this location corresponds to time 2 seconds, let us say 0, 0, say, yeah, this is at 0, that is at 1 second, and you have traveled another, and you are trying to find out the disturbance at, say, 2 seconds, and then at also 3 seconds. Okay. So when you are moving at speeds which are far less than the speed of sound, okay. So if your Mach number is far less than 1, which is like velocity of your flight vehicle is far less than velocity of sound. Okay. So in that case, let us say at time t0, at 0 seconds, you have created a disturbance. So that disturbance travels in the form of, so after 1 second, so this may not coincide. See, this is don't get confused with that. So at 1 second, or say when you are at 1 second, right, this disturbance might have traveled a distance a. Am I correct? A times 1 a here. So when you are at 2 seconds, this has traveled a distance. So this can be much. So when you are at 2 seconds, this has traveled a distance. I mean, this disturbance has traveled a distance 2a. Right? So this 2a and this scale are not equal. Please don't get confused. So this disturbance the propagation of this disturbance keep increasing as the time lapses from your, right, this thing. Yeah, from the point where you started the disturbance. So in order to make it better, what I'll say is, so say still this is 2s, right? So okay, so this is your assume the center of the circle is this point at 0 seconds, and you are trying to figure out at after, say, 1 second, 2 seconds, and 3 seconds. So this has traveled a distance 4a, right? So sorry, 3a. Okay. So when you are at 3. So after that, what happens? So after 0 seconds, you have already created a disturbance which is 2 seconds before, right? Am I correct or not? At this particular location. So if you draw another, so this will travel, when you analyze it at point 3, this will travel a distance of 2a. Am I correct? So when you are here, that means you already passed, I mean, you already spent 3 seconds. Within the 3 seconds, the disturbance which you have initiated at a location, at this particular location, will travel a distance 2a, isn't it? So similarly, the one here, it will travel a disturbance, the disturbance will travel a distance a, 1a, which is 1 second ahead at this particular location where you are, right? Isn't it? So that means the disturbance is always ahead of you. Am I correct or not? Because so the radius that you can travel within, or the distance, say, will be V infinity times delta t. This particular distance will be V infinity times delta t. So delta t is 1s, and V infinity is far less than that particular a in that particular regime. Am I correct or not? That is what we have it here. V infinity is far less than a. So the distance you might have covered is far less than what the disturbance might have already progressed. Am I correct or not? So that means the molecules which are far ahead of you, of your location, will get the information about your presence. Okay. So which have enough time to get adjusted with the shape of your body, so that the flow can happen, or the fluid elements can smoothly flow over the body. Right? The streamlines have enough time to get bent around your object, right? So they get the information about your presence and the kind of pressure disturbance that you are creating, right? The fluid elements which are far ahead will have that information. So, but when you are traveling with a higher velocity, let us assume you are traveling with the velocity of sound. Let us consider a case. So, this is like at low or subsonic, or at subsonic speeds we can say. So this is the condition at subsonic speeds. Okay. So when you move at the velocity of sound, let us say, so the distance, what do you mean by that? So let us say you have started at 0 seconds, no? You created a pressure disturbance at 0 seconds. So the distance it will cover within a second will be equal to, let us say this is 1 second. So this distance is equals to the distance that this sound wave propagates, isn't it? Or the pressure wave propagates here, pressure pulse propagates. Am I correct or not? Why? Because you are also moving at a velocity equals to, say, when you are moving at Mach 1, which is velocity of your flight vehicle is velocity of sound, right? So within 1 second, you are here and the disturbance has also traveled, which was initiated here, a distance A times T, which is equals to V times delta T. Here delta T is 1, right? So the same disturbance when you are at 2 seconds, right? So what will happen to the same disturbance? You are there. Am I correct or not? So let us say you traveled 1 more second, you are at 3 seconds, the disturbance you have is again a concentric circle and you are on the circumference. Concentric circle about O here. Am I correct or not? And this particular at 1 second location, you have also created a disturbance. So after, when you are at 3 seconds, this will say have 2A, isn't it? Am I correct or not? So the diameter of this will be 2A, diameter of this bigger circle will be 3A. And at 1 second, it will have A diameter. So this the difference between this is 1 second, right? So a second before your current location, you have created a disturbance, and this disturbance also traveled a distance here. So that means, so at each and every point, you are with the disturbance. You are traveling with the disturbance, right? So the air molecules. So let us say if you draw a tangent to this particular point, so the air which is ahead of this particular point will not have any information about the object which is approaching those fluid elements. Okay, so that is when we call this as a Mach wave, right? So that Mach wave will create a lot of changes to the free stream velocity in terms of pressure. There will be a huge pressure increase as well as temperature and also the density. And downstream of this Mach wave, what we have is decrease in velocity, right, compared to that of upstream velocity. Okay. Now let us consider, so this is at sonic speeds. So let us say this is A, B, and let us say this is at C is at sonic speed. Right. So let us now consider a case when you are moving faster than the speed of sound there. So what happens when you are moving faster than the speed of sound? This will be interesting, right, isn't it? So let us consider this is the path that you are moving, right? So say this is at 0 seconds. So 1 second location. So let us not say now this has 1 second location, because you are traveling at a higher speed compared to that of sound. Otherwise you can still say that 1 second location. So by the time you reach this, the sound will not reach this particular 1 second. So because your velocity is far higher than this particular sound velocity. So the sound, this 1 second may not be appropriate here. Let us say A1, right? Let us say or capital capital A1 is the location, first location, right? Another location which you have reached within some time, say, okay? But the sound may not be able to, that sometime may be T1, right? Okay? So the sound may not, the distance propagation will be A times T1, whereas you have covered a distance V infinity times T1 which is higher than that of A1 times T1. Okay? Why? Because you are flying at higher velocities, so supersonic velocities, where your velocity is far higher than the velocity of sound. Okay? So A times, not A1 times, A times T1. Now, so when you reach point B or A2 here, what happens is, so, okay, at A1 again you have created another disturbance. Okay. So when you reach point A2, this A1 will travel certain distance, right? That again depends upon the difference between this and the time. So when you are at A1, or say by the time this sound reaches this A1, you have already crossed this A1. Right? And by the time the sound reaches A2, you have already crossed A2. That means the disturbance is always behind you, right? Similarly, the disturbance that you have created at A1, by the time it reaches A2, you have already reached ahead of A2. For example, consider this case. So now let us consider the propagation of this disturbance. So let point O at 1s, 2s, 3s, right, and you are at some other location here, right? The initial one which you have, like at point O, the disturbance that you have created, so may travel a diameter, right, which is the velocity of sound times the disturbance here. In the second one will also be, right, velocity times the delta t here. And the third one again will also be velocity times delta t, right? So the diameter at each and every point will be the velocity times the corresponding time lapsed, right, since you have created the disturbance. Okay. Now, see, because no disturbance will be able to overcome u. Why? Because you are traveling at a higher a compared to this. Now, let us say if you draw a tangent to all these disturbances, what you get is a cone. Right? So if you draw, so this is not exactly to the scale. That's the reason why we may not be able to get the tangents properly. But say if you draw a tangent to all these circles, okay, so this particular angle is known as mu, which is the cone angle here, right? So this forms a Mach cone angle. Okay, so where sine mu is given by, sine mu is what? Opposite by hypotenuse, right? This is so this is tangent and this is the diameter which is perpendicular to the tangent. What I have is A times delta t upon V infinity is the velocity at which you are traveling, times delta t is what you have, if you have reached this particular location. This is Vt times delta t. What you have is 1 upon m, right? So mu is equals to sine inverse 1 upon m, Mach number, m infinity, right? What we call it as Mach cone, right? So that means all the disturbance that you can see is limited or confined to this particular Mach cone. So if you are looking at the 2D profile of this, you can say wedge, Mach wedge, or when you are looking at the 3D profile, it becomes a Mach cone. Okay, fine. So all the disturbance is confined within this Mach cone. So whatever, like for example, whomsoever stay outside this particular Mach cone will not will not get to know any disturbance. So to understand that, consider an example where a person is standing on the ground, right? So a supersonic aircraft has already passed him, okay, and he is not able to hear any sound from it, right, until he gets into this Mach cone. Okay, so by the time he hears this, he is already the aircraft has already passed him. Okay. So what you call this as, so this is a supersonic aircraft, let us say. This is called zone of action, and this is called zone of silence, where there is no disturbance. The disturbance is not propagating ahead of this. Okay. So whoever are inside this is the Mach cone, or we can say Mach cone, let us. So whomsoever which are inside that Mach cone will be able to feel the disturbance, but all the fluid elements which are ahead of this Mach cone will remain in the silent zone. So due to the lack of this propagation of this disturbance, the fluid elements which are just ahead of the aircraft will hit the aircraft instead of flowing smoothly over the aircraft, right? Which was the case for subsonic flow. So the same will not happen here anymore. The fluid element doesn't have any information about the presence of the object in the fluid or the disturbance that is created by the object in the fluid, right? So instead of passing slowly across the body, right, it will try to hit the body abruptly. So the molecules there will feel a shock, across that, like as soon as it encounters this aircraft. So those molecules will encounter this aircraft by means of a shock. So in a lower subsonic speeds, what happens is the flow will smoothly flow over this object. The fluid elements will smoothly flow over the airfoil at subsonic speeds. At supersonic speeds, what happens is, if the leading edge of the airfoil is sharp enough, then you'll have an attached shock to it, right? So if the leading edge is sharp enough, you have attached shock. So if the leading edge is blunt, you will end up seeing a detached shock. For sharp bodies, for sharp leading edge. For blunt bodies, this one. Blunt leading edge. Okay. So as soon as the fluid particles crosses this shock, so there will be huge variation in pressure, increase in pressure, temperature, as well as density. Okay, and the velocity downstream the shock, as I told you, is always less than the velocity upstream the shock. Okay. So this pressure is nothing but like the compression of those mass of the fluid particles which are ahead of this flying object, right? So this compressed fluid particles will offer additional resistance to its motion, right? So that additional resistance to the motion, apart from the skin friction as well as pressure drag, is the wave drag. Okay, so the wave drag is due to that skin friction, that additional resistance by the fluid particles across the shock, for the aircraft to move in that particular fluid. Okay, so that's a story about this wave drag. Yeah. So this profile drag coefficient, if you look at the profile drag coefficient, so I'm talking about profile drag coefficient here. So if you look at profile drag coefficient, it will almost remain constant with Mach number, right? So until certain Mach number called drag divergence Mach number. So beyond which there is an abrupt increase in the drag. Okay. Increasing Mach number. So until certain regime, the change in the variation in CD naught or profile drag, what you can say is profile, CD profile. So the profile drag coefficient will remain constant, or can be considered, the variation is very insignificant in this till certain Mach number called drag divergence Mach number, beyond which there is an abrupt increase in the drag coefficient, profile drag coefficient, right? So that is the Mach number at which the change, or there is an abrupt increase in this profile drag coefficient, is called drag divergence Mach number. So when you look at subsonic speeds, what happens? Consider a point P here, right? A local point, or say the minimum pressure point on the airfoil. Let us say that. So if this velocity, which is less than 1, so on the surface it will increase definitely compared to that of free stream velocity here, isn't it? That's what we studied till now. And then if the velocity is, let us say, is close to a higher subsonic speeds or close to sonic speeds, right? Let us say, though it is not close to the sonic speed, the speed stream velocity is not close to the sonic speed, but still if it is higher or close enough to the sonic speeds, what happens? The even when you are flying at a subsonic speed close to sonic, right? M is equals to 1, okay, close to. So what happens is the local flow accelerates and you will see a shock wave on the surface of this wing, right? So the local subsonic speeds at which the airfoil or the aircraft first encounters a Mach wave or a sonic speed is known as critical Mach number. So you are still at a local or subsonic speeds, but your wings see a sonic boom on it, or or a shock wave on it, or you can say you see the local velocity will reach as Mach number 1. Right? So that particular Mach number at which you're flying, or the Mach number of that flight, is considered as critical Mach number. Right? So critical Mach number and drag divergence Mach number are two important parameters that we need to talk about. So critical Mach number is, in general, less than drag divergence Mach number. So though you are flying at, so again, you have to delay this critical Mach number as much as possible. Why? Because as soon as you see the critical Mach number on the surface, you see on the surface of the wing, you see a higher speeds, right? So maybe, yeah, of course, critical Mach number corresponds to sonic speed on the surface of the wing. So that will create a shock wave, which will increase the drag, right? So aim is to reduce that drag. In the previous problem, we saw that when we want to fly at higher velocities, once you solve it for different velocities, you get to know that you need more drag to overcome. You need more force to overcome the drag, because the drag increases, and the requirement or the input to the system has to increase accordingly. So the main aim is to decrease this drag. So there are various ways to decrease this drag again, right? So we are not going to discuss about that here, but I want you to understand what is critical Mach number and what is drag divergence Mach number. So critical Mach number is the local subsonic Mach number at which the aircraft first encounters sonic speed on the wing, right, on the wings. And drag divergence Mach number is the Mach number at which the profile drag coefficient start a rapid increasing, right? Sees a profile drag coefficient will see a rapid increase, right? So that is a drag divergence Mach number. Okay, see you. Thank you.